Hello everyone and welcome back to another tutorial on TURBOMOLE. In this tutorial, I'll be showing you how to perform a simulation of a nonlinear optical phenomena such as high harmonic generation using real-time time-dependent density functional theory as implemented in the Ripper module of TURBOMOLE. High harmonic generation is a nonlinear process where an intense electric field distorts the atomic potential, allowing the electron to tunnel out. The electron then moves and accelerates under the influence of the electric field. When the electric field switches sign, the electron starts traveling back towards the parent ion and can recombine to release a photon with a frequency that is an integer multiple of the original electric field's frequency. And this is why high harmonic generation can be used to generate attosecond pulses. The high harmonic generation spectrum usually looks something like this. We have a perturbative regime where the harmonics decay quickly, then there is a plateau region where the harmonics have roughly the same intensity, and finally a cutoff region after which the harmonics die out completely. In this tutorial, I'll show you how to calculate and plot such a high harmonic generation spectrum for the water molecule. In TURBOMOLE, the laser pulse is defined using the equation as shown on the screen. Here, E naught is the amplitude, omega naught is the frequency, and F is an envelope function, with sigma being the FWHM. So you will add the following to the control file. You will add an electric field as shown over here, and then provide the amplitude, frequency, and FWHM of the electric field in atomic units. For this tutorial, we will have the laser pulse polarized along the z-axis of the water molecule as illustrated over here. Usually in the literature, one mentions the intensity of the laser pulse rather than the amplitude. You can convert the amplitude to intensity using the equation shown here. This expression relates the electric field amplitude in atomic units to the intensity in watts per centimeter squared. For this tutorial, we will use an intense laser pulse of intensity 30 terawatts per centimeter squared, which corresponds to an amplitude of 0.02923 atomic units. You can also use the unit conversion module of the Ripper Tools web app to obtain these numbers. For the frequency, I'm using a value of 0.0456 atomic units, which corresponds to roughly 1.24 electron volts. For sigma, I'm using a value of 1379 atomic units, which corresponds to approximately 10 optical cycles. This means that the duration of the laser pulse we are going for will be 20 optical cycles. Finally, we will also provide some details regarding the RT-TDDFT simulation in the control file. For HHG simulations, it is recommended to use the SEF time propagation algorithm. We will evolve the system for 2758 atomic units, which is twice the sigma value. So we evolve the system for approximately the same duration as their pulse. Then RT dipole and RT energy in the control file indicate that we want the dipole moments and energies to be printed at each time step, which is crucial. Okay, so now we are ready to run the simulation. So here I've already created a directory with the required files. I have a coord file and a control file over here. And note that I will be using a minimal coord control file, so you will need TURBOMOLE version 8.0. The coord file contains the atomic coordinates for the 3 atoms of the water molecule. And then the minimal control file looks something like this. So it contains the information of the coord file name. Then we specify the basis set and the auxiliary basis set. Then we specify the DFT functional to be M06-L, which is a local meta-GGA functional from the Minnesota family. Next, we specify the convergence criteria for energy and density. After that, we have the fields and RT-TDDFT blocks that we already discussed. And now we will go ahead and run the simulation using the command nohup ripper_smp right arrow output.ripper %. And now if we press ls, then we can see that there are now many more files in the simulation directory compared to before. And we can see that the output file shown here contains information about the RT-TDDFT simulation as well as the electric field. We can also see the dipole moment at the end. In order to track the simulation progress, we will use the command tail-f RT energy, and this will show the energy at each time step. Since our simulation is running for 2758 atomic units with a time step of 0.5 atomic units, we will get information for about 5516 steps, and this can take some while, so let's skip to the end of the calculation. Okay, so the calculation is now complete and we can see that it took about 32 minutes, which is pretty quick. Next, in order to plot the HHG spectrum, we will need the RT-dipole file, which contains the time-dependent induced dipole moment. It looks like something like this. It contains the induced dipole moment along the X, Y, and Z axes for each time step. Now we will head over to the Ripper Tools web app and click on the HHG Spectrum Calc and Plot button in the sidebar menu. And here you will see that it allows you to set various parameters such as the field, amplitude, laser pulse frequency, FWHM, along with the details. Right now these fields are pre-filled with some sample values, and there is also a sample RT-dipole file already loaded here that is being used to plot the spectrum. Now we will go ahead and fill these fields with our simulation parameters. I will get these values from the control file and paste them here. Next, I'll copy the contents of the RT-dipole file and paste them into the web app as well. Once pasted, the past values are displayed in a table and can also be downloaded as an Excel file. We can also see the plots of the dipole moments along the X, Y, and Z axis. Only the Z component shows the same behavior as the electric field, since the electric field was applied along this axis. Then we leave the remaining settings at the default values and scroll down to see the harmonic generation spectrum. I will turn on the option to display grid lines, and now we can see the harmonics are integer multiples of the fundamental frequency. We can also see the typical perturbative regime, the plateau regime, and then the cutoff region. We can also adjust the y-axis limits to make the plot look better. Finally, one can download the plot as an image, and it looks something like this. The spectrum's X and Y data points are also displayed as a table and can be downloaded as a text file. So that's it. In this tutorial, I showed you how to calculate and plot the harmonic generation spectrum of a water molecule using the RT-TDDFT implementation within the Ripper module of TURBOMOLE. I hope you found this tutorial useful. In case you did, then don't forget to hit the like button and subscribe to the channel for more videos like this. And thanks for watching and have a great day.